Let's get started with our phenomenal opening headliner. She's a faculty member at Mila and an associate professor and William Dawson Scholar, as I've said, at the School of Computer Science at McGill, where she co-directs the Reasoning and Learning Lab. She's also a co-managing director of Facebook AI Research, where she actually oversees labs in Montreal, Seattle, Pittsburgh, and Menlo Park. Her research focuses on developing new models and algorithms for planning and learning in complex, partially observable domains. She also works on applying these algorithms to complex problems in robotics, healthcare, gaming, and conversational agents. Ladies and gentlemen, I am absolutely thrilled to hand you over to Joëlle Pineau, who will be here to talk to you about transforming personalized healthcare with AI. And just before we dive in, if you would like to join Joëlle after her presentation to just learn more and ask her some questions and unpack some of the issues she's about to touch upon, please head over to her masterclass taking place in the workshop and panels tab, where you can post questions in the chat, or if you're feeling bold, go live with video and sound, whichever you prefer. So without further ado, I'd love to hand over to Joëlle.
Thank you, Fiona. It's a pleasure to be here with you all today. I'm based in Montreal, but really happy to be reaching many of you wherever you may be and share some of the work that we've been doing. Most of the work I'm presenting today is work that has been done with students, collaborators at McGill University and some of the related university hospitals. We've heard a lot about AI in the last few years, and in particular, there's been a steady stream of results hitting the headlines about how AI is going to profoundly transform healthcare. And really leveraging the power of data and the power of algorithms together to enable better prediction, better decision-making in the context of medicine and clinical care more generally. Now, this is all really, really promising, but in reality, there's sort of a virtuous circle that is necessary between the theoretical work and the practical work, really relating very tightly what we do on the research with what we are seeing in the hospitals, in the medical clinic, in public health, and so on. And so a lot of my work is really focused on this tight integration of research and practice, but also very, very close collaboration with AI researchers and clinical researchers. And really, I think if there's one thing to take from today, it's really to keep in mind that by having these close collaborations and this fertile exchange of ideas and best practices between the researchers and between the practice is how we make some of the most progress. And so I'll be sharing with you a few of our ongoing projects and stories. And at the very end, I will also speak about some of the broader ethical issues that surround this work. And for those of you who want to dig deeper into these topics, that will be the area in which I'll go into more depth in the masterclass that follows. And so to bring you along on the story of some of these projects, I need to tell you a little bit about my particular domain of expertise in research, which is reinforcement learning. Now, the idea of reinforcement learning dates back several decades in the field of psychology, where the early behaviorists have posited that by training an agent through a presentation of rewards and consequences, you can actually shape the behavior of this agent. And so for anyone in our audience who may have children or pets at home, this is actually quite a familiar concept, the fact that you can shape the behavior by offering rewards that are paired with the types of behaviors you want to reinforce, and perhaps some penalties or punishment associated with the behaviors you want to diminish or extinguish. And so when we look at this, and my training is really as a computer scientist, as an engineer, when we look at this, the idea is that taking these principles, we can actually transform them into algorithms, into mathematical models, and use these to train our computers, our algorithms, to make better decisions. So exhibit behaviors that are going to maximize reward. And so we have a whole set of mathematical models and algorithms that encode these basic principles. And these environments is sort of the decision problem over which the computer or the robot has an influence. And the role of our AI system here is to select a sequence of actions that is designed to maximize the reward. And to inform the choice of actions, the agent has access to perception, observation, the kind of information that flows into the system. So on the basis of this framework, and again, I'm sharing it with you sort of conceptually, but when we look into it in our own research lab, we have a whole set of mathematical models and algorithms that are associated with this. But on the set of this principle of reinforcement learning, over the last few years, researchers have shown some phenomenal success at using reinforcement learning to train computer agents to play some very complicated games. We've seen some really nice success training with reinforcement learning some computers to play Atari games, a whole set of different Atari games, really, really classic. We've also used similar techniques to build a system to play Go, the Chinese game of Go, at a level exceeding the best human players. We've seen it used to play poker and so on. So a lot of really impressive results in games. What's really quite particular in games, and we'll come back to healthcare in a few minutes, but what's quite particular in games is that we always know very clearly what's the outcome we want to achieve. We want to win at the game, and the definition of what's a win is very simply expressed in a language that the machine can test and understand. This is all well and good, and I love games as much as anyone else, but quite frankly, what has drawn me to research in engineering and computer science is really the potential to leverage algorithms to solve problems that are fundamental to the well-being of humans and society. And so I'm most driven to explore the potential of reinforcement learning for all the many other applications that arise where we do need machines, computers, robots to be making decisions that are leading to good outcomes. And so over the last few years, we've seen a new stream of applications for reinforcement learning to be able to inform how we do things like, crop management, how we build tutoring system, how we build systems that can do fair trading of energy, and so on and so forth. And so the potential of this framework is enormous. The algorithms are often designed initially for the simple settings of games, but as we broaden our scope and as we go into this virtual circle between theory and practice, we have the potential to develop AI systems and impact a much wider range of applications. And so going back to the topic of healthcare, let me share with you one of these specific projects from the last few years where we applied reinforcement learning to enable better decision-making in a healthcare system. This is a project that I've done in collaboration with researchers at the Montreal Neurological Institute over several years. These are people who are experts in understanding the dynamics of epilepsy. So epilepsy is a neurological disease which unfortunately affects upwards of about 1% of the population, one of the most prevalent diseases. And there's several ways to treat patients with epilepsy, the most common being through a pharmacological, so medication treatment. Another alternative being surgery, which, as you can imagine, is quite invasive since it affects the human brain. Third line of treatment, which is increasingly used, is the notion of neurostimulation. So the idea is that you can implant a stimulation device, usually implanted in the chest cavity, but with electrodes running into the brain. These electrodes, some of them are sensing the neural activity in real time, so reading the EEG signal. This is what I'm calling the state here, the information, the observation in real time. And there's other electrodes that are able to deliver electrical stimulation to the brain. The theory of this, and this is the actions that you're seeing over here, the little red dots indicate the timing of the stimulation. The theory says that by particular placement of the stimulation, you can disturb the neural activity of the brain. And in doing that, you can minimize the occurrence of seizures. And so, it's quite a promising technology, but as you can imagine, it requires a really delicate application of that simulation. You don't want to overstimulate the system, destroying the ability for the brain to execute its normal function. You don't want to understimulate, because when you do that, the brain in these particular patients gets into a sort of a pathological pattern that leads to seizures. And so it's really about figuring out how can you get the right dosage between stimulating at the right time based on the information you're seeing. And so that's really the problem we pose to our reinforcement learning system. Can we learn through trial and error to stimulate at the right time point in order to minimize the occurrence of seizure, but also minimize the amount of stimulation delivered? When we build a system like that, we rely on the literature in the field. And so in our case, I'm showing you really briefly, the watershed of contributions on reinforcement learning in the AI literature from the last 30 years or so. In the early days where reinforcement learning was first introduced, just a few papers a year, recently upwards of 20,000 papers coming out every year on this topic. So it's really quite intimidating to figure out how to choose the right techniques to solve your problem. Nonetheless, we sort of plunged in and selected some methods that we thought were promising. But it's interesting to keep in mind that when we develop these systems for real world application, we don't always pick the latest and the best in terms of the literature, because sometimes there's particular characteristics of your problem domain that require a different choice of solution. So this is also part of the story for this morning. Bringing you back to our application, as most AI system, we're looking at machine learning approaches. So we are training from data. I'm showing you here a quick snapshot of the type of data that we had. Each of these lines indicate a particular stimulation pattern that was applied. So at first, in the control period, no stimulation was applied. After a while, we start stimulating very slowly at 1 hertz, 0.1 hertz, so every 10 seconds. And then we slowly increase the amount of stimulation that gets delivered, trying to figure out what's the optimal time of each stimulation. So we had data in this case from a in vitro model of epilepsy. So it's slices of rat brain that we use for these experiments. As it's very experimental, of course, we don't start with human subjects from day one. So we had 8 of these slices from which we could do some recording. We could try these different stimulation patterns of increasing intensity. And we feed this into our computer. What I'm calling fitted Q iteration here is actually the algorithm that's going to distill the information and try to make the prediction. This algorithm, this fitted Q iteration algorithm we used, is actually based on random forest. So for those of you in the audience who are perhaps more familiar with machine learning techniques of the last decades or so, will probably have seen these random forests. It's interesting to know we didn't use the latest and the best in terms of these neural network model with deep learning and so on, for the specific reason that in this case, we have relatively little data. It's much smaller data when you deal with healthcare applications than a lot of the other work that you hear about in AI. We're not really in this very big data regime. And so that forces us to take algorithms that have the ability to perform well, even with relatively small data. These random forests happen to perform quite well with small data. They also have very few hyperparameters, and so they're very stable to the setting under which you do the training, which is incredibly valuable when you target one of these real-world applications. Having taken our data, trained our algorithm, we next move to the phase of trying to test this. And in this particular case, we used about a dozen slices to try out the stimulation that had been learned from the machine learning algorithm. And we were looking for 2 things. One of them, we were looking, have we shown that we can reduce seizure more effectively than with other approach? And fortunately, the answer we got to this was yes, we could actually reduce the amount of seizure down to almost 0. And secondly, have we shown that we can use less stimulation than with other approaches? And there also, fortunately, the results of our work showed that we could use about 70% of the amount of stimulation compared to other approach. So combined together, we had reached our goal of both observing fewer seizures and using less stimulation. Now, it's interesting to look at a little bit the timeline of a project like this, right? We spent about 6 months on the initial data collection. We spent another 6 months or so configuring the algorithm, training it, and then 24 months or so really just doing the testing and the validation and really showing with strong certainty that we had achieved the result that we wanted. And so compared to other applications of AI where people really get the sense that, oh, we have this box, perhaps a black box, perhaps a toolbox, we apply it, feed it with data, and out will come these predictions. It's important to realize that there's actually a really long stream of work in some cases that's necessary, both to make sure that you have the right data, that you train the algorithm in the proper way, but also that you do the validation to have a high level of confidence and credibility in your results. Moving beyond this project, one of the next phases is to figure out, can we, not only do well in these simplified in vitro models, but actually apply the technology to live models, either live animal models or live human models. There's many things that make this quite challenging in terms of the type of data, in terms of the variability of seizures that we have to compose with. And last but not least, we have to be really careful about ensuring that we don't see poor performance of the algorithm, because we're dealing with a much more sensitive system. And so the level of safety and responsibility that we take on when we carry this work is incredibly important. Now, I've talked a little bit about using this in vitro model. It's interesting to know that one of the directions where we're seeing a lot of activity going forward is in building models that we can use for training. And so not always relying on, for example, an in vitro system, but actually using data to build a model to essentially simulate the dynamics of a brain and be able to use the simulation model to train our AI agents and then use that solution. And so that's one of the directions where we're seeing a lot of promise going forward. But we have to be quite careful about the characteristics of the model that we build. And of course, that's one of the big challenges lying ahead for the field. Speaking of building dynamic model, let me share with you a little bit of the progress we're seeing on the horizon, specifically in this question of how do we generate synthetic data in a way that is convincing, in a way that is accurate. And so we've seen a lot of progress in the last 3 or 4 years on the data generation front. I'm sharing with you a very simple example dating back a few years already. So this is not so state of the art, but it's to give you a sense of how we go about doing this. The idea of these data generation models is that you can take a lot of real data. So I'm showing you some real images on the left. In the case of our own project with neurostimulation, it would be real recordings of EEG from patient. We feed this into a model such that then we can sample, so get the model to generate new data that looks really realistic, but is not real data. And so what you're seeing on the right side, all of these model samples are images. To the human eye, they look perfectly functional and reasonable. In reality, all of these images are completely synthetic, generated from the pixel level by an AI system. And so this particular technology has been used to all sorts of use cases. If you're looking at the 2 images I'm showing here on the top left, these are images of faces. In this case, both of these, though they look incredibly realistic, are completely synthetic, generated now by a model. And it's quite impressive, the quality of the images that we are getting over the last few years. And so though we have seen some really, really realistic images, people have also used this technology in all sorts of really creative ways to generate images that, in this case, in the lower case down here, imitate the style of painters and so on and so forth. So it's interesting to see this dual use of such technology. We've seen this in other domains than AI. We're also seeing it here, where on the one hand, the same model can be used to generate fake images of people, but also to really enhance the creative toolbox of someone who wants to create fantastic images. Within the our own work, we have used similar technology actually from the medical point of view. So this ability to recreate data is at the basis of a system that's been built for reconstructing MRI images. So for those of you who have had an MRI scan taken, you know how long and somewhat oppressive it can be to be in these machines who take very careful images and sort of reconstruct this 3D model. Through the similar algorithm that do generation of images, we've been able to take MRI samples that are really spaced out and reconstruct the rest of the data so that we can acquire an image of the same quality 4 to 8 times faster than with traditional MRI machines. So really promising to see that when we have some of these models developed in one modality, images, we can take them to another modality, medical imaging, and really get some impressive progress in terms of our ability to construct high quality information in this field. One final project I'll share with you is a project we've been doing over the last year. You know, as with all of you, we've been affected deeply by COVID-19. As researchers, we were somewhat privileged to having the ability to try to contribute to the fight against COVID-19. And so we've built some collaboration in the last year with several hospitals in Montreal as well as in New York, trying to analyze the data from COVID patients, trying to look if we could make better prognosis for these patients directly, in this case, from X-ray images of the lungs. And so we have the ability to observe images from patients and try to see whether from these images we can predict which patients will require intubation, might require going to the ICU, and so on. We've heard a lot about the large number affected by COVID-19. From a machine learning point of view, it's still, especially in the early days, we started this project last March, last April, the number of observations we had from patients was still relatively small. And so we were able to build a machine learning system that first did a pre-training phase with chest x-rays that were of non-COVID patients. And what's interesting here is we're using a similar procedure as the doctors did. Most of the doctors who were called on to treat COVID patients hadn't seen x-rays from COVID patients in the early days, and all of their training had been done with other data. Similarly, our algorithms were first pre-trained with non-COVID patients, but other respiratory conditions. We spent a lot of time with those data because we have larger data sets of that. And then we have a final fine-tuning phase where we use the COVID patient data to improve the algorithm and really up our ability to do prediction. So at this stage, we have high-quality prediction from the images comparable to the accuracy of doctors. Where the AI systems don't quite match the doctors is in their ability to integrate other information. So looking just at an X-ray, the AI is quite good, but in terms of integrating all the other clinical variables, the lab tests and so on, it's sort of the next step in terms of our development of these models. Concluding the talk for today, and for those of you who want to continue the discussion, please join me for the masterclass in a few minutes. It's really important as we engage in these applications that we think not only of our scientific and engineering responsibility, but also the social responsibility of deploying the system in a way that's consistent with our human values. So I'll be glad to go into a little bit more of this topic in the masterclass. Just a few final thoughts. First of all, really recommending a tight integration of theory and practice to allow fast innovation. And for me as a researcher, grounding our work in real world application is really very, very promising way to ensure that we make progress in a way that's both scientifically responsible, but also socially responsible. With this, thank you very much for joining me. It's been a pleasure to be here, and I wish you all a good day.
Wow. Well, thank you so much, Joëlle, for what was really a fascinating overview of some really important work.